All right, so welcome to the second lecture today. Sort of hope that it's the last snow day lecture. So sun is shining outside. Hopefully everything will melt soon. So let's look at the. Oops, I have the wrong pen. So let's look at the convergence of sequences of holomorphic functions, right? So the next subsection in the book. So the question is, what is the right topology for holomorphic functions, right? Kind of the natural topology. What is the topology that first comes to mind if you have holomorphic functions, right? And I mean, on sets of functions, there, it's always going to be a bunch of different topologies depending on what you're trying to do. But if you just say holomorphic functions, there is actually the topology that first comes to mind, right? And this is, if you're an analyst and you are given a class of functions, you want to know what's the topology on this class of functions, right? What's the right topology on this class of functions? Interestingly, the right topology is the same one that is the right topology for continuous functions, right? I mean, if you look at the set of continuous functions, continuous function, on some finite dimensional space, generally, the one that you say, oh, that's the obvious topology is uniform convergence, and really you just need uniform convergence on compact subsets. So basically, we say that a sequence of functions, Fn converges uniformly on compact subsets to some limit whenever for every compact k, right? So given any k that is a compact subset of U, that we have that this sequence of functions Fn restricted to k converges uniformly to F restricted to k, right? So on each k, it's uniform, right? So of course, it's not going to be necessarily uniform in all of U, all right? You might have to, so if you want to get closer to the limit, if you're closer to the boundary really of U, then you might have to go further, right? But that's the topology, right? Now, what do we mean by the right topology? Is the one that preserves this class, right? I mean, you always want to have some sort of a completeness, right? So that if I have a limit, right, that the limit is still back in the class, right? That's the most most natural requirement, right? We could ask for a stronger topology, but we're generally interested in the simplest topology that does that, the most natural one, right? And that, for continuous functions, right, it's one of the first things that you learn in undergraduate analysis when you're looking at sequences of functions, right? Uniform limits of continuous functions are continuous. So it's the same one for continuous function, which is weird, because it's not the same thing if you're talking about, let's say, real differentiable functions. If you're talking about, like, let's say even, continuously differentiable functions on R, right, or on some interval in R, it's not the right topology. So, for example, if I look at this guy over here, and there's lots of other examples, then this guy converges uniformly on compact subsets. Let's say on any interval containing the origin, it converges uniformly, or any bounded interval containing the origin, it converges uniformly to the absolute value x, which is not C1, but this guy over here is actually continuously differentiable, right? And you can even do, like, infinitely differentiable example. There's lots of examples, right? You can have by Weierstrass's theorem, for example, any continuous function is a limit, uniform limit of polynomials on any interval, on a bounded interval, and sort of so polynomials are going to be the sort of the nicest, most differentiable, really amazing functions, right? They have all sorts of properties, right? And you can take sequences of those that have as the limit an arbitrary continuous function, like this incredibly evil behaved continuous functions, right? Something that, for example, might not be differentiable at any point, right? So it's something that's very specific to holomorphic functions, right? There's a lot of connections between sort of the right thing for continuous functions is the right thing for holomorphic functions. That happens quite a bit. All right. So let's prove that this is the right topology. So suppose that I have a sequence of holomorphic functions and they converge uniformly on compact sets to some function f. Then f is holomorphic, right? Now, it's not just that. This is an amazing thing that happens is that once you get that these guys converge uniformly to some f, not just that f is holomorphic, but actually you will get that all the derivatives immediately, right, also converge to the derivatives of the limit, right? I mean, the limit is holomorphic, so it has all these derivatives, right? But you get automatically you get this uniform convergence, right? Now, this is maybe where how to really think of this is if I had, like, let's say infinitely differentiable, like real differentiable functions, the right topology there is you want essentially all the derivatives to converge uniformly, right? And that would be sort of one way to to get a smooth functions, right? Well, here that's the thing. I mean, you get that for free, right? You only need to figure out that that the functions converge uniformly, and you immediately get all the derivatives do the same, right? So interesting, right? All right, so let's prove it. So we're going to prove this in 2 bits. So first, let's prove this f is holomorphic. So let's prove that it's holomorphic at some point. All right, so let's call that P, and let's consider a little closed disk such that the whole closed disk is in U, right? And well, because these are the fn's are holomorphic, we have Cauchy's formula, right? So we can write this, integrating over the boundary of this little disk, right? Now, we really want to take the limit, we want to take the limit as n goes to infinity. We can take it easily on the left because, that converges uniformly to f. So in particular, pointwise to f. So, if we take the limit on the left, yeah, we're good. We're at f, right? And we want to take the limit over here. So that's what we want to do. We want to be able to move the limit from the outside to the inside. So we know that the limit of this thing exists, right? I mean, it is f, right? We're just trying to think, can we move it inside? So we know that the boundary is compact. So in particular, one of the consequences is that if I take the distance from z to the boundary, it's some positive number, right? So let that be a positive number. Well, that would be that positive number, right? Let delta be the distance. What happened there? Okay. Now, let's do a little bit of an estimate, right? So if I have let's basically fixing z, right? I mean, it's, it was really a fixed z at this point. Zeta is going to move, right? Zeta moves in the as we're integrating, but we look at how is this function going to converge, right? How are the functions underneath the integral going to converge, right? So it's this function as a function of zeta, and it's supposed to converge to this function. Well, we know that it converges, right? Because it's at least pointwise, but is it uniform, right? Is the question, right? So you you rewrite that like this, right? When really is inequality. I'm not sure why I'm writing an inequality over here. So you rewrite it like this. I mean, it's fine, but it's actually equal, right? And then you estimate the bottom, right? Because you have the distance from z to, this is, the boundary is where zeta is, right? So zeta is in the boundary, right? So it's I basically get that zeta minus z is bigger than or equal to delta, right? Because that's the boundary, right? So if I take 1 over everything, right, I get this, right? I get the inequality going in this direction, right? And I get that this is bounded by this thing. Okay, and now basically we're done. Well, at least with this bit, because that means that these guys, as a function of zeta, right, converge uniformly to this guy, to f over zeta minus z, right? So it's uniform on the boundary, right? Because why? Well, this thing is compact as well, right? I mean, we have that Fn converges uniformly on compact subsets, right? So if this goes to 0 uniformly, therefore, this thing goes to this thing uniformly. All right. So that means that we can take the limit to underneath the integral, right? And what do we get? We get this thing, right? Essentially, we're getting this is where the sort of the converse to Cauchy is coming in, right? But it's really just applying that term, right? I mean, we have that that f is equal to an integral of something which is holomorphic in Z, and therefore it's holomorphic, right? So we get that. Oh, right. I should say that this thing is continuous by uniform convergence, right? So I mean, we do have that. I mean, f itself is continuous, right? So that we can actually do this, and so I apply the Cauchy transform to the boundary values here, and I get that f restricted inside has to be holomorphic, right? Okay, so f is holomorphic, right? Because I mean I can do this at every point. We still need the moreover bit, which is the the maybe a little bit more surprising bit, maybe not, I don't know, but it's definitely a surprising, or it should be surprising, and that's a little bit more subtle to prove. So basically, let's take a compact set, right? And this is actually a useful technique that comes up often. I have a compact set and some sort of uniform convergence on compact things, and this a lot of times when we're writing things in terms of an integral of the values in a neighborhood, this is going to be a technique that comes up. So all right, so suppose that we have a compact set. We're trying to get that we can get the Lth derivatives, right, for any L are going to converge uniformly on this K. And it's not going to be so trivial, because we have to actually get another compact set. So So basically, let d be the distance of k to the boundary, right? And well, k is compact, so this is some positive number, and if there is no boundary, right? If u is the entire complex plane, you just take an arbitrary number, right? Arbitrary positive number, right? But if it is, if there are some points in the boundary, right, take it to be the distance, right? And now we enlarge this k over here. We enlarge it to some k prime by basically taking the union of all the closed disks of radius half the distance to the boundary, right? So we're definitely, this k prime is clearly a subset of u, right? And it clearly contains k, right? So it clearly contains k, and it's clearly a subset of u, right? This is sort of a typical picture, right? I mean, this is one of these one of these disks is marked over here, right? And if the distance to the boundary of u is d, right, this basically goes halfway, right? So at the closest point of k to u, you still would go only halfway. Maybe over here you go, it's further out to the boundary, but you still go only d over 2. That's going to be good enough. Just some distance, actually, anything positive that still stays in u really is what we need. So the next thing we want to show is that k prime is compact, right? Well, it's clearly bounded because, well, it can't go further than d over 2, which is some number further away from the origin, right? So if you have a bound for k, add d over 2 to it, and you have a bound for k prime. So it's definitely a bounded set. Let's show that it's closed, right? Which is not quite immediately clear, right? I mean, it's an infinite union of closed sets, and that's not immediately clear that that's necessarily going to be closed, but in this case it is. So suppose that I have some point not in k, right? So I'm going to show that there's a little ball, right? At some point over here somewhere, right? Now there is going to be, so maybe let me use the other pen. So maybe I have, it doesn't have to be in u, well, whatever point that is not in not in k prime, right? And we're going to show that there's a whole ball around it that's still not in k prime. So there's definitely a q that's closest, right, to this p, right? So this is the p, this is the q, right? So there's a q in k, right? Maybe more than one, but at least one, right? Right, and this p minus q, right, is the distance, right? So it's the closest one. Okay, now it's going to erase all my drawings. So if we have, right, this is where I have to redraw this, just unfortunate way this works. But I have this, sorry, that was P. This was P. Q was the one over here, right? Now, this distance, right, is definitely bigger than d over 2, right? Because, well, it's outside, right? I mean, this distance is d over 2, right? This is definitely further out, right? If it was less than or equal to d over 2, it would be in k prime by definition, right? So therefore, p minus q minus d over 2, this guy over here, right? Maybe now I can switch back to the highlighter. This guy over here is a positive number, right? So that means that this is a nice open disk, right? it's a nice open disk around P, right? And all these points, by maybe triangle inequality or something, are further, well, actually by triangle inequality, not or something, by triangle inequality, are further than d over 2 from k, right? Because, well, maybe let me actually move back to these things, right? So because this, if I go and I have p over q minus d, I'm really sort of, taking this whole, it's supposed to be a disk, right? This whole disk, right? It's open disk, right? But everything, any point over here, right? I mean, this guy, right? I have, right, so this distance, if I really went sort of the shortest route, I would, I would sort of end up at, exactly this distance away. But points at this distance away are not in this ball, right? And any other point, I'm going to get something longer, right, by triangle inequality. So, right, so that's, that's what's happening here. So, therefore, we have that K prime is closed, and since it's bounded and closed and it's a subset of C, remember, closed and bounded is not the same thing as compact, right? But as a subset of a finite dimensional Euclidean space, yes, then it's fine, right? So it's closed as a subset of C, and it's bounded as a subset of C, which is R2, so it is compact, right? So in Rn, this is a fine thing to say, but I want to make it clear. Somebody's going to say this on some homework. I'm pretty sure. Closed and bounded implies compact. We're going to get to places where that's not true, right? So in this case, it is. It's a subset of R2, right? Subset of C. Right, so we have that it's compact. Now, we have that Fn converges uniformly on this compact set, right? Because it converges uniformly on compact sets, right? So notice that we started with a k, and we're asking for Fn now to be converging uniformly on k prime. We needed to converge uniformly on a slightly bigger set, but that's fine. Right, so we have that given epsilon, there's just some n such that we get epsilon close whenever we're in k prime and whenever n is bigger than capital N, right? That's just uniform convergence, right? So now, let P be any point in K, and we apply the Cauchy estimates to this function, which is a holomorphic function, on a ball, or on a disk of radius d over 2 around P, right? So that means that the Lth derivative of this function, right, can be bounded. These are the Cauchy estimate, right? The size of the disk to the Lth power, right? And there's this L factorial, I guess, in the Cauchy estimates, the L I don't have the pen, but anyway, the L factorial is in the in the denominator here, right? So I'm just moving it to the other side, and we have the uniform norm, like the maximum modulus of f minus fn on the boundary of this disk. However, this boundary, right? Well, it's part of this guy, right? P is in K, right? So this entire disk, it's one of these disks over here, right? And it's entirely in K prime, right? Including its boundary, right? So I have this estimate, right? Because I have it for all z in K prime, right? So therefore, I can bound this guy by epsilon, right? And I've moved it 2 upstairs. It doesn't really matter. This maybe get rid of the. So this is just a constant, right? Because we're doing like for any L, we get uniform convergence. So L is fixed. So who cares about what this is? D is also fixed. That depends on K, right? That was the distance of K to the boundary. So everything out here is just a constant, right? So we've shown that this guy, given epsilon, there is a, there is an n such that for all n bigger than n, we get that that this is less than or equal to something that's some constant times epsilon. So we might as well have made that epsilon, right? If we asked for a smaller epsilon over here, right? Divide by this guy over here, right? But so that's good enough, right? So that means that we have uniform convergence of this sequence of functions on K, right? So notice how this proof works. You start with a K. You get to you have to enlarge it a bit, right? You use the uniform convergence on this enlarged guy, but then basically it's that you can write down the derivatives as an integral of these fn's. That's it's all Cauchy's formula. It's the Cauchy's formula for the derivatives, right? For the right, when we differentiated the Cauchy formula, right? So we had essentially we have a equation for these guys, right? And that's in terms of the values of the function on a little circle, right? And as long as that little circle stays inside some compact set, we're good, right? So we get uniform convergence on this K in terms of uniform convergence on this K prime, right? So we get uniform convergence on K in terms of uniform convergence of the values of the function, right? On K prime. Or uniform convergence of the derivatives, sorry, on K is in terms of uniform convergence of the values of the function on the little bigger set. So this is a very useful argument. It comes up actually quite often. So it's good to understand it. All right. So right, as I said, the point is that we can write all the derivatives, including f itself, as integrals of f, right? And over some circle, right? So you can get at the derivatives by integration. And integration is much nicer, right? If you want derivatives to converge, if you want derivatives to converge, you basically need them to converge, right? If you want to have a function that whose derivatives also converge, you need those derivatives to converge, right? You need more than just uniform convergence, on the values of the function. But if you're integrating, you just need uniform convergence, right? That's why this works, because we can write down everything as an integral over some circle. We just have to sort of massage everything so it works out how we're writing it. But that's essentially what it is. We get the convergence because we're integrating. So we're passing the limits past the integral, and for that we only need uniform convergence. All right. So that's it. So hopefully we'll be in person next time.